Hello and welcome to Unit 3, Lesson 3 on Newton's second law. This is the third and final example of this lesson. And in this lesson, it's the most complex question of the three. I'll go on and I'll read the question here, and then we'll jump into solving it. So the question gives us a 2 kilo box with 3 forces acting on it, and it tells us the magnitude and direction of 2 of the 3 forces, and we are to solve what that third force is going to be. Now there's one extra piece of information that this gives us, and this extra piece of information is right in the question, and it says the acceleration is 35 meters per second squared west. So then we're going to determine force 2 and the unknown angle. And force 2 is this unknown force value down here. So this is what we are solving for, that and this. Okay, so a few things I want to maybe sketch on here before we get too involved. I'm going to sketch on a direction compass. Alright, and I'll label this north, east, southwest, and we might as well put on our positive and negative directions on here as well. So I'm going to make up positive, east positive, right? Positive in the y direction, positive in the x direction. And these will be negative in the y direction, negative in the x direction. Okay. What do we have to do next? Well, we should also write on here the acceleration that this gives us, because that's going to be a useful value. This is becoming a fairly complicated diagram, but really all that's going on is we have our block, we have 3 forces pulling it, 2 of them are at angles, 1 of them is straight to the right. Okay, our acceleration is 35.0 meters per second west. So it's going to be on this diagram to the left. Alright. And I'll label that acceleration equal to 35.0 meters per second squared. Okay. Before we jump into any math on this question, let's just look at it and analyze it a little bit. Alright. This acceleration value, if we're looking at the topic of this lesson, Newton's second law states if an object experiences unbalanced forces, the object accelerates in the same direction as the net external force. What this acceleration headed due west is telling me that if we were to draw our resultant triangle, right, our resultant triangle would only have a net force to the left. There would be no up or down. Cross those out. Okay. There is no y value to this. It's due west, which means that the force in the y direction pulling upwards is going to balance that of the force in the y direction downwards. If we're talking about our topic 2, I believe, which was equilibrance, the y values are going to have an equilibrant value here. The force downward in the y direction is going to be opposite but equal in magnitude to that of the y direction on force 1. So that we have a side length, we have an angle. I believe this is going to be a sine law question to find the y value there. Alright, so that is one thing we can knock off. But before we get going, I want to just discuss the other value that we can do in terms of the x direction. Since this acceleration is purely x, we're going to be able to figure out the x value of this line along here by using cosine rule, right? This is going to be cosine. We have an angle, we have a side length, so we can solve that value. We're going to have F net with the acceleration and the mass, and we're also going to have force 3, which means we're going to have 2 forces, the F net. We have 1 missing force. So really we're going to be able to find the x value of this and the y value of this, then we can just use some Pythagoras theory. Okay, let's now that we've talked about how to solve it, let's actually solve it. So the first thing that I want to do is I want to solve these side values. Okay? We want to split all of our angled lines up that we can into x and y values first, because we can't do anything with these angled values. Always split these up into their x and y. Okay, so f1, let's start with the y value. Why not? So let's say, choose a new color, magenta, and this is f1y is going to be equal to 150 sine, because it's opposite, 150 sine of 25 degrees. Okay, and we plug that into our calculator, and I get a value, or a magnitude, of 63.4. And that's in newtons, and I will say that is up. Or our direction scheme here is north. Okay. f1x, we can do almost the exact same thing, except we're going to be substituting in cosine. So we have 150 cos of 25 degrees. It's equal to, and also if you're confused about the trig rules, I do in my earlier videos flesh out all of the math for the trig rules. It's some math skills that are required to get to this level, so maybe go back and review them. I'm sorry that I'm not doing them here, but I'm trying to keep the videos a little bit shorter now. Okay, anyways, 150 cos of 25 degrees is equal to 136 newtons, and this is out to the left, and our left is west, so we can say that this is west. Ultimately, when we start plugging that into our net force formula, this is going to be a negative value. Okay. So, what do we have now? We have this 63.4 newtons north, and we know that in our y direction, let's do y direction is red, why not? Yeah, I'll show the math to this. I don't have it written out on my sheet, but let's go f net in the y direction. Oh, you know what we should do? No, we don't need to do that yet. F net in the y direction is equal to 0, because this acceleration is going due west. There is no upward pull or downward pull. Sure, there's two forces pushing upwards, but this block itself is sliding down the road straight west. So there is no y value here. So we can say that it's equal to 0. And then if we do our f net formula, where f net y is equal to f1y plus f2y, right? This is f1y, and this there would be f2y. These two magnitudes are going to be equilibrants to one another. And so, let's say 0, which is our f net y, is equal to f1y, which we solved here. 63.4 newtons north. North is positive. 63.4 newtons plus f2y. Do some rearrangement here. f2y is equal to negative 63.4 newtons, which turns into 63.4 newtons south. Okay. That is almost half the problem done. Let's jump into the x value. Okay, so x value is a little bit more involved. Let's change our color up to represent a different value. We haven't done math in blue yet, so let's switch our math up to blue. Okay, so our f net x, we're talking this direction. Our full f net is going to be x, right? So since this is purely traveling in the x direction, we're going to say that this is equal to mass times acceleration. We also did, for this one, when we got 0, we also did mass times acceleration, except our acceleration value for y was equal to 0. So this whole thing became 0. Okay, back to f net x. So mass times acceleration. So our net force is going to be 2 kilos times 35.0. Which comes out to 70 newtons. Whatever. I'm not going to put the decimal on here. Okay. Force net, 70 newtons to the west. So again, when we plug this in, that's going to be a negative 70 newtons. Okay. So we've done our first F net formula. Now let's do our second F net formula, right? The sum of all the forces. So maybe I'll put a little breaker on here, and then we'll say F net. It's going to be a little tight on space for this question, but that's okay. F net is equal to force 1. Oh, and I want to put the x's on here, right? These are x's the whole time. Is equal to force 1x, correct, plus force 2x, which is the one we're solving for, right? We want to find, we have this f2y already. We're trying to find now f2x. And once we have this value and this value, we can just do Pythagoras theory to find the final side length. Okay, plus f3x, which is this value, all x. All right. Let us plug in some numbers to here now. Negative 70 newtons west is our net force. So negative 70 is equal to F1x. Have we solved that? Yes, we did. We solved it up here. It equals 136 newtons west. So negative 136 newtons. It's negative because it's in the west direction. Plus f2x, which we're solving for, so we don't have that yet, plus f3x. Really the only one that was straight up given to us, and that's 80 newtons east, so that's a positive value. So we're going to add 80 newtons. Okay, do some flipping around, some algebra, that's the word I'm looking for, and we solve f2x, and I get for f2x, 1 second, I don't think I have that exact value. I could just store that in my calculator. So we're going to have negative 70 plus 136 minus 80. Gives us a value of negative 14 newtons. Okay, f2x equals negative 14 newtons. Or we can call that 14 newtons west. Okay. Right on. So we have a couple values. We've got f2y, which is here, moving down. we've got F2x, which is here moving to the left. Excellent. The directions match what we'd expect. Now we just have to find the magnitude and the angle. So, let us, you know what? I want to draw a tip-to-tail diagram, even though we have this small diagram here. I think that it's good practice to always redraw our net force triangle. So, let us draw out our 14 newtons to the west. So we'll do that here, try to conserve a little space. 14 newtons. And what color did I use there? It's kind of like a dark red. So downward, we have this 63.4 newtons south. Remember, always tip to tail. This is not to scale because my 63 would have to be much longer. Okay, and what is the value? 63.4 newtons. Perfect. Which means now that our resultant force line is this one right here. And that's what we're solving as F2. So this is, try to turn that off. F2 is equal to what? Cool. Well, do some Pythagoras theory. So a squared plus b squared is c squared. So c is going to equal the square root of a squared plus b squared. Again, skipping steps. Hopefully by now you're familiar with how to do Pythagoras theory. So c is going to be equal to the square root of 14 squared plus 63.4 squared. It's getting a little messy, I'm sorry. So our magnitude works out to 64.9 newtons. So magnitude is done. This angle here, right, if we look at this diagram, is the same as this angle here. That's theta. We also need to solve that. So we have 14, we have 63.4. That's just a simple little tan calculation. So let's do our little tangent calculation here. Theta, wow. Theta is equal to the inverse tan of opposite over adjacent, so 63.4 over 14. So theta is equal to, I get 77.5. Yep, 77.5 degrees. And if we need to put a direction on there, this is coming out from the west, moving down to the south. So this is south of west. Okay, so final answer is, I'll write this out. Well, it's a good color. We haven't really used red except for the diagram. So F2 is equal to 64.9 newtons at 77.5 degrees south of west. And that is the end.